Okay, let's talk about guidelines for balancing chemical equations. The first is start balancing from a substance with the most atoms associated with it. Secondly, if polyatomic ions are present in the chemical equation, we want to balance those as one unit. Third, we say free elements for last to balance. And then the fourth thing is to remember this, that balancing chemical equations is a trial and error process. All right. So let's look at two examples here in which we balance the chemical equation, and definitely going to utilize the guidelines here. So here we have propane C3H8, and on this side we have one carbon and we have two hydrogens. Well, I'll put a 3 over here in front of this carbon, so now that gives me 3 carbons on this side. And to get 8 hydrogens on this side, I will put a 4 here. Alright, so now I'm going to save the free element for last, this diatomic oxygen, for last to balance. So 3 times 2 is 6, so that's 6 oxygens here. And then 4 here, 6 oxygens. And then 4 times 1, that's 4 oxygen. So that gives me a total of 10 oxygens on this side. So what I would do to get 10 oxygens on this side, so I'll just write 10 oxygens here on this side. I'd put a 5 in front of this diatomic oxygen, so 5 times 2 would give me 10 oxygens on this side. Alright, and so I have 3 carbons, I have 8 hydrogens, and I have 10 oxygens on this side. Remember, we treat this arrow as an equal sign. So over here I have 3 carbons, I have 8, we'll put carbons here, I have 8 hydrogens, and I have, of course, the 10 oxygens here. So I am balanced by mass. Whenever, according to the law of conservation of matter, we have to balance the chemical equation both by mass and by charge. Okay, there are no charges here that we are confronted with, so we're just balancing this chemical equation by mass. So that simply means I have to have the same number of atoms on both sides of the chemical equation. And so if I read this chemical equation, what this says is that for 1 mole of propane, I need 5 moles of diatomic oxygen to react with that to give me 3 moles of carbon dioxide gas and 4 moles of H2O gas. All right. Let's look at this other equation here. This is butane, which is typically found in cigarette lighters. They use butane. It is a liquid, not a gas. Okay, this is typically a liquid, not a gas. All right, so we'll start with the one that has the most atoms, and that's butane. So I'll come over here to the product side. I have 4 carbons on the butane, so I'll write 4 in front of CO2 here, right here, and then I will write, let's see, 10 hydrogens on the reactant side, so I'll write a 5 right here, and that will give me 10 hydrogens on the product side. So I'm saving oxygen, diatomic oxygen, for last, right? So I'll do a count here. I have 8 oxygens here, 8 oxygens here, and then I have 5 oxygens here. So that gives me a total, 8 plus 5 is 13, so that gives me a total of 13 oxygens here. So I need 13 oxygens over here. So if I have, there's no way I can put a 13 right here and that would ultimately give me 26 oxygens. But if I said 13 divided by 2, that would be what, 7.5, no, 6.5, I'm sorry, 6.5 times 2, and that would give me 13 oxygens. But we don't like how this equation is written, this fractional form here. And so I need to get rid of that fraction. And so what I'll do is I'll multiply the entire chemical equation by 2. And when I do that, check this out. That gives me 2 moles of butane, and that's liquid. I'll write the states here. And then I get 13 moles of diatomic oxygen. And then that gives me 8 moles of carbon dioxide gas. And then that gives me 10 moles of H2O gas. All right. So now I'll do my atom count. I have 8 carbons on this side. I have 20 hydrogens on this side. And I have 26 oxygens on this side. And so I should have that same number of carbons, hydrogens, and oxygens on the product side. So let's see, that's 8 carbons on this side. And that's 10 times 2 here. That gives me 20 hydrogens on this side. And I get, okay, this is 16. 16 times 10 times 1, that's 26. So that's 26 oxygens on this side. So I am balanced. All right. So these are just some examples of how we balance chemical equations. We will definitely look at some other problems as it relates to balancing chemical equations in the next slide. Okay guys, pause the video and see if you can balance these 3 chemical equations. Okay, so you paused the video, hopefully, and you tried balancing these chemical equations, these 3. Alright, so let's look at this one. We have iron metal reacting with carbon dioxide gas to give us iron 3 oxide, which is rust, plus carbon monoxide gas. Alright, so we'll start here. We'll use this as a starting point. Alright, I have 2 irons over here, so what if I put a 2 over here? And that will give me 2 irons on this side. Alright, so notice I have 4 oxygens over here, but I have 2 oxygens over here. Now, if I put a 2 right here, then ultimately that's going to give me 2 carbons on this side. So what I need to consider doing, maybe, right? What if I put a 3 right here? And that would give me 6 oxygens on this side, 3 carbons on this side. So if I put a 3 right here, then that will give me 3 carbons on this side and 6 oxygens on this side. So let's do an atom count here. We have 2 irons, we have 3 carbons, and we have 6 oxygens here. Alright, and so that's going to equal to 2 irons, right? Give me 3 carbons, and that's going to be 3 oxygens here and 3 oxygens here. So that's going to give me a total of 6 oxygens. So I'm balanced. Alright, let's look at the next one. We have carbon dioxide gas reacting with H2O. This should be in the liquid state. and that gives us glucose, right? This is glucose. This is photosynthesis, all right? Photosynthesis, which is what plants undergo. As you know, there is a symbiotic relationship that exists in nature. Plants take the carbon dioxide and water and convert it to, via photosynthesis, converts it to glucose, which is the food it needs. And we also get oxygen, which is the air we breathe. So put some plants in your house and get you some oxygen, right? And cleanse the air a little bit. Okay, but at any rate, we'll start with glucose since it has the most atoms. So we got 6 carbons in glucose. So we'll put a 6 right here. And then we have 12 hydrogens in glucose. So we'll put another 6 right here because 6 times 2 is 12. And so now we'll save oxygen, which is the air we breathe, right? We need oxygen to survive. So we have 12 oxygens. 6 times 2 is 12. So we have 12 oxygens, and then we have 6 times 1 oxygen is 6. So that gives us a total of 18 oxygens. So I have 6 right here, 6 oxygens right here. And so all I have to do is put a 6 right here, and that gives me 12 oxygens. So 12, 6 times 2 is 12, plus 6 is 18, and voila, there we go. We are balanced, guys. All right. So we have 6 carbons over here. We have 12 hydrogens, and we have 18 oxygens on this side. Remember, I told you to treat this arrow as an equal sign because we should have the same number of atoms on both sides of the chemical equation, right? So we have 6 carbons over here, and we have 12 hydrogens, and we have 6 plus 12, 18 oxygens over here. And so we are balanced by mass. So we're in compliance with the law of conservation of matter. All right, this is the last one we're going to do here, and I hope you got some of these right when you pause the video. Here we have barium nitrate. So this is the nitrate polyatomic ion. And we have hydrogen sulfide. And these two react to give me barium sulfide solid and nitric acid in the aqueous solution. Alright, so we have 2 nitrate ions over here on the reactant side. So what if I just put a 2 right here, and that would represent these two, the 2 nitrates, right, that we see over here. So we're using this as one whole unit. Remember what we said about balancing the polyatomics treated as one unit, and so that's what we're doing here. We have 2 NO3s over here, so we'll put a 2 in front of the nitric acid to give us 2 NO3s over here. Alright, and so let's see what else we have to balance here. We have 1 sulfur, 2 hydrogens here, 2 hydrogens over here. It looks like we're balanced, guys. Alright, so we have 1 barium. Alright, we have here 2 nitrogens. We have here 6 oxygens. We have 2 hydrogens. And we have 1 sulfur. And then we'll draw our equal sign. So here we have 1 barium. We have 2 nitrogens. We have 6 oxygens. 2 times 3 is 6. And we have 2 hydrogens. 2 times 1 hydrogen is 2. and we have 1 sulfur here. And so yes, it only took 1 coefficient for us to balance this chemical equation. Sometimes they're just that easy, and then other times they can be a little more involved. And that's why we say balancing chemical equations is a trial and error process. Practice at this. The more you practice, the better you become. And always remember never to mess with the subscripts, okay? The only way you can balance a chemical equation is by adjusting the stoichiometric coefficients, all right, in front of the substances, all right? So I hope this video was helpful. Again, these are just a few examples to help get you started and build you some confidence in terms of balancing chemical equations. And we'll see why also we need to make sure the chemical equation is balanced when we talk about reaction stoichiometry. So more of that to come.